All right, we're going to wait just a minute or two, everyone. For the guys that are here so far, we're just going to let everybody filter in for another minute, and then we'll go ahead and get started. All right. Thank you, everyone who's joined already. Today's nTop live session is going to be a bit of a Q&A. So if you have questions, please, if you're watching on YouTube, throw them in the chat. If you're here on the Zoom, go ahead and put them in the Q&A section. We're going to try and answer as many as possible. To begin, however, I went through the education Slack channel that we have. If you're not part of the education Slack channel, please go ahead and go to nTopology.education/join Slack. If you follow this URL, you'll be able to join our Slack channel. That's where we can answer your questions, and that's where I got a lot of the questions that I'm going to go over today. I have some pre-prepared files, and I am going to go over those. Just to start off, a question came in. Someone's new to nTop. I'm not going over the exact basics today, but we do have on the 23rd a nTop Essentials session coming up. So if you're interested on exactly how to run everything inside of nTop, go ahead and join into that session. You can already register for it up on our website. All right, to start off, I saw a lot of questions about the FEA workflow inside of nTopology. Quite a few specifically about meshing and some other stuff. So we're going to start off with that. You can see on the screen here, I have just a single unit cell that I created of an FCC unit. Pretty basic. I thickened it to 1 millimeter. And what I want to do is show you a really robust way of meshing this inside of nTop. When you start getting into the hundreds or thousands of unit cells and using field-driven design to vary them, you can start getting troubles when you're meshing. This is a really good way to go about meshing these structures, and it's pretty new to nTop, so some of you might not know of it yet. If I type up in here, it's going to be Voxel Grid from Implicit Body. Now, one other question I saw was, what happened with the switch from nTop Body to Implicit Body? nTop Body was an Implicit Body, but to alleviate any confusion, we switched the name to Implicit Body. So now everyone understands that an Implicit Body is in the implicit format as an nTop Body was. So no more nTop Body, just Implicit Bodies. Getting back to our Voxel Grid, what this is going to do is going to create a Voxel Grid out of our implicit here. You notice I have this in implicit format because it's asking us for a body. So if I were to pass something that wasn't implicit, it wouldn't be about input. So we can drag and drop that guy in there. We can specify our voxel size. Again, I denoted these thicknesses as 1 millimeter to try and really capture this guy shape as best as possible. We'll do something like maybe 1/4 of a millimeter. And what you'll notice is here we have our voxel grid created out of this. And now if you've ever tried to mesh these lattice structures before, you know it can be pretty tricky. But you'll see here, this is a really, really good mesh representation of this. I'm sorry, not a mesh representation. This is our voxel grid. To take this further, to use it in a finite element analysis, as we're going to do, we need to convert this voxel grid into a mesh. Notice this is gray here, and this is our meshes. As you'll see here, if I do mesh from voxel grid, you see our meshes are a bit more orange in color, and that's just one way to do it. So all I did was drag and drop that voxel grid into mesh from voxel grid, and now it's in that mesh format. It didn't change any of the voxel gridding that occurred. It just converted it from a raw voxel grid into a mesh. Now, this voxel grid is just a surface mesh, so we need to take it a little further. But not only that, you can see it is a hex mesh where it's got square elements. Inside of nTop to do volumetric analysis, we need a tetrahedral mesh, so we need to convert it into that. And we can do that pretty quickly and pretty easily with a remesh surface block. So what we've done so far is we've taken our geometry, made sure it was in implicit format, created a voxel grid, and then turned that voxel grid into a surface mesh. What we're going to do now is turn this surface mesh into a triangular surface mesh. I'll grab a couple of these here. All right. Now let's denote our edge length. We said our voxels were 1/4 millimeter, and it's a pretty good representation. So let's go ahead and start off with also having a 1/4 millimeter edge length and our triangular elements. Now this is going to go ahead and run. And you'll see it went ahead and regularized our mesh into these triangular elements, which is exactly what we needed it to do. One thing I like to do, this might help you when you're creating those meshes, is come over here to your edge length, right click it, make it a variable. This is going to alleviate some problems down the line when maybe you're refining your mesh. You don't want to have to go into a couple different blocks. You're just going to have this variable. Super helpful little trick. Now this is still just a surface mesh, although it's now in our triangular elements that we need. We need to turn it into a volume mesh. And that is just done with our volume mesh block. So we need to take our nice new mesh that we created from our voxel grid and put some elements inside the volume. So we're going to go ahead and drag and drop that. We have this variable we just created. We want those to be the same. So we have equally sized tetrahedral elements on the interior of our volume there, and let it create that volume mesh. Note, nothing changed on the screen because everything that happened on the inside of this volume. Now, to use this for our finite element analysis, we need to turn it into our FE volume mesh. And I have this already here. Drag in, drop. We now have a linear FE volume mesh that we can go ahead and use in the static analysis. To do a static analysis, however, we have to define some boundary conditions. What we're going to do in this case is talk about the differences between these selection types. A lot of questions were asked about the difference between FE boundary by body, FE region by body, and FE boundary by flood fill. Take a note here where I have these two selection types. FE body by flood fill is not on this list. That's just due to the fact that we're going to take a look at this here in a little bit, and that's when we're going to look at the flood fill specifically to show you just a little bit more about what you can use with that flood fill. All right. So to create our forces or our fixed supports, we need to select nodes to apply those boundary conditions to. So we're going to start off with our FE boundary by body. Our FE boundary by body is going to ask us for a mesh. It needs to know what mesh we're going to look on to select these nodes. We double click in here, where we can drag and drop our FE volume mesh right there. Our nodes, we want to make sure it's selecting nodes in this case. You could select edges or faces, depending on what you're doing. In this case, we're going to select just nodes. And body. So what it's looking for in this case is an implicit body that is intersecting our mesh at some point, and it will select the nodes that are intersecting both inside the mesh and that body that you put. So if you double click in here, I have something called top already created. And all top is this box that intersects just the very top of our unit cell here. Now, if we turn his view off, turn on the view of our boundary, you can see it selected those nodes on the top of our mesh here that were intersecting the implicit body of our box. So that's how you would use this FE boundary by body. You can take this a step further, and inside of our static analysis, we could denote a force here on all of those nodes we selected. Taking a look at our FE region by body, this is a little bit different. This is not for selecting nodes that we're going to apply forces or displacement restraint to. This is more towards selecting a region inside your finite element mesh. What do I mean by that? If we take a look at just, again, this unit cell we have, and I have a box called left. What this is going to do is it's going to select all of the cells, shells or beams. In this case, we're going to select our shells that are intersecting this box and the FE mesh. What that looks like is this green selection here. where we have all of these cells that were intersecting that implicit body and the FE mesh at the same time. This can be used a couple of different ways. I'm going to show you one way down here at the bottom. If you take a look at this cube, just a cube I have just to represent this, where we're actually going to define different material properties in different regions of this cube. We're doing that here. You can see FE boundary by body. Where on this right half here, I actually denoted that material properties in these cells should be titanium 64, the common titanium for additive manufacturing. Whereas the left-hand side here, the material properties in all those cells are that of Inconel 718. So this is one way where if you have a lattice and you don't want to try and mesh that lattice and simulate the whole thing, you could give some representative material properties to it. Or if you're going to do something like a topology optimization and you are going to use passive regions, you would use FE region by body to select those passive regions. Moving back to our unit cell that we have here, we want to take what we did. We created that mesh. We used our FE boundaries to apply a force on the top and fix the nodes on the bottom. I used, for the displacement here, I also just used a FE boundary by body, which again, all I did was intersect the box on the bottom and apply displacement restraint to all those nodes. And if we take a look, you can see here, I have our von Mises stress map up. We were able to simulate this lattice structure using our Voxel Grid mesh, which was, as you saw, pretty quick, pretty easy to use. We can take a look at our displacement. We could toggle back on our mesh if we want to see how things are displacing. We have our values. We can switch between our displacement and our stress values and everything like that. Now, a lot of you guys also asked, not just how do I get better meshes? How do I mesh these complicated parts, but how can I take these meshes into an external solver like ANSYS? So I want to show you guys what we have here, these export blocks that I have below our static analysis, where if we wanted to export our FE model, which would be our mesh and material properties, you can see the options here. We have quite a few. ANSYS, for ANSYS mechanical, you'll use a CDB file, or for ANSYS Fluent, you'll use your MSH file. The workflow to get it into there right now would be something more along the lines of this, where you create that CDB file and you go into your directory and you know where it's at, and you first open up this mechanical APDL block inside of your workbench. You need to do this because what we're going to do here is open up our APDL block, and I just have a pretty common, just a beam to show you guys. You bring that CDB file inside of this APDL block, you go to preprocessor and you rewrite it. So what we're doing here is we're rewriting this CDB file into the newest format that they need. And when you, if you're going to rewrite this, you want to make sure you come down, select all finite element information. You're going to save this to the directory you need it to. You're going to remember where you saved it, because if you don't remember where you saved it, that could be problematic. Close out of this guy. And then the next step is to open this external model block and then open your CDB file you just created in this setup part and correspond that to your model input. So if we open up our static structural here, which might take a little bit of a second, you'll see that we were able to import that CDB file that we created inside of nTop, brought in here, and we're going to be able to use it inside of our ANSYS mechanical. Close this guy out. Then in here, you'll be able to select the faces, so you can put your forces, your displacements, or anything else. One thing to note, at the current point in time, you can't bring node selections or face selections, so you need to be cognizant of that. But you will, we're currently and always working to improve that workflow. So in, I think, 2.8, we'll have the ability to bring node sets into here. So you'll be able to select nodes inside of nTop, export all that together in the CDB file, and you won't have to go through this APDL step. You'll go right to this external model step, bring it into there, and then you can use your named selections for your nodes to set up your boundary conditions. Example of that, close out of this guy, open up our test block. And this was going to show you that you can bring in those named node selections. All right. And now this file I created from a CDV file that I exported from the newer test version of nTop. You can see we don't have that APDL step that I talked about. We're able to skip that, go right to our external model, and directly link it to our static structure. Then you can open it up and you'll be able to bring in node sets. And we're going to be working towards bringing in element sets as well. As I mentioned, we're always working on improving that workflow. So that's definitely coming here in the near future. All right, now I just brought in this little cube just to keep it nice and simple. But if we go up to our name selection, you're able to see that I brought in this node set on the top here, where I was able to apply our force. We look at our static analysis here. Applied a force to these nodes, and then we also held these bottom guys fixed. And we ran our analysis to get our stresses. So this is coming. Hold tight. It'll be here soon. But some of you also asked about, what about CFD? What am I going to do if I need to bring in, a .msh file so that I can select my input and outlet surfaces? We're working on that as well. I'm going to show you an example of what you can do today inside of nTop to get it into our ANSYS Fluent. But you're going to have a similar step. Apologies, that one's not working, but you're going to have a similar step where you're going to need to bring in your .msh file into the .msh file that you export from here. You're going to bring in this .msh file into your ISOM, and then from there you can select the elements to create your inlet and outlet faces for your CFD analysis. And then you can directly put it into your Fluent. All right. That's where we're going. Again, just keep an eye out. We are going to be constantly updating that. We're really working hard on making that as best as possible. Transitioning back a little bit, let's talk about the FE boundary by Floodfill. What is it? How do we use it? Taking a look at this, we actually have just a pretty normal bracket here, and we want to run a static analysis on this guy. Well, in this static analysis, we fixed, let me bring this guy back up. We fixed these two faces here. We fixed all the nodes on those faces, and we actually applied a force on this upper face here in the downward direction. How did we do that? We used the FE boundary by Floodfill. The way the Floodfill works, if I open this up here, you're gonna note it's asking for a mesh. It still needs to know what mesh it's looking on. It's asking what entity again, nodes, edges, faces. This time we're looking for nodes, origin. So where is this Floodfill gonna start from? The way it works, and we have these points here where it's gonna take this point as its origin point, radiate outwards, and find those first nodes that it finds on that boundary in every direction, and then it's gonna use those nodes. So it's radiating outwards from this point and finding those nodes on the boundary. Now, this is really, really powerful in some ways where, say we want to make a design change. Now, this is a completely separate imported part. So normally you would have to come in here, select your faces again, make sure everything's good to go, and then it would run. But with a Floodfill, we can go ahead and X that out, grab the body of this new part, and it's going to radiate outwards from these points again, grab those nodes, and it's going to rerun the entire static analysis for us, just this quick. So now, not only have we used a different type to select our boundaries, we are actually able to automate our workflow here. So we can see we've got displacement, moving that way, we've got our stress, we've got everything here. It was just that easy. So in a general sense, the Floodfill is taking that origin point, radiating outwards, and finding those first nodes on the boundary that it hits. All right. Let's take a look here. You guys asked quite a lot of good questions. One question I saw asked Let me check the Q&A section. I want to make sure I'm not missing anything for you guys. Okay. Okay, awesome. So before I get into this file that I have open here, we had a question come in. What is the difference between TopOpt and generative design? Why did we choose TopOpt? The way we like to think about TopOpt is it is a subset of generative design. So we're not choosing one or the other, we're generating our design using the topology optimization workflow. So we like to see it as they're both in a way similar. A question came in about this previous file where I used the Floodfill. Let me transition back here. The question was, what is the purpose of applying the force to the nodes rather than the faces? The purpose in this case is the force is going to distribute. Let me open up the force here. The force is going to distribute this force vector that we denote here in the positive x direction across all those nodes. Where if we applied it to the face, it's going to apply it normal to every single one of these nodes. So it's really useful for like a pressure application if you're selecting faces. It's just a different way of selecting nodes. In this case, we selected the nodes instead of the faces for our application. So if you want to select those faces, it's just application dependent in that sense. All right. Let me make sure I'm not missing anything. All right. If you have any more questions about our TopOpt workflow or generative design or anything like that, we have a blog post from last year, and let me grab this for you guys, where we go into a lot of depth, and it was covered by one of our brilliant engineers we have working here. Let me paste this in chat for you guys. And he goes over all of this in some good detail. All panels, and there we go. If you check out that link that you should be able to see inside of the Zoom chat, or if you go to our website into the section where we have our blogs and scroll down to the blog that I believe is called Topology Optimization in a World of Fields and Implicit Geometry, we talk about the differences in generative design, topology optimization, and how nTop works with all of that. So if you want to give that a read, please do. I do recommend it. It's a very good read. All right, continuing on a little bit. Another question I saw in the Slack channel just a couple of times, and I was actually emailed in by one of you guys specifically for this section, was, can we perforate holes in any body normal to the surface direction? The answer to that is yes, we can. You'll see here, I grabbed some earbuds, brought them in as a mesh, because what we need to do here is put some random points on this mesh. And you can see with these points that we created, not only did we vary the hole size here, we also varied the spacing of our points. We did that with a couple of our ramp blocks in our random point. If you come here, we used a ramp to change the spatial weighting of our points. And then inside, once we have these points, what we do is we create a branch lattice. So we're offsetting these points, normal in direction, out and inside. So we have 2 points here, and we create a branch lattice between each of those 2 points. So you'll see we have this little list with a start and end point. So we actually have 3,000 individual branch lattices that we created from these points. And what we do is when we combine these lattices into one singular one, and we do a variably thicken. So that's how we did the variable sized holes here. You notice, again, they're all normal. And so the way we did it was we created that custom branch lattice and then used that to poke the holes in the normal direction. There's a little bit of cross products going on in the background and that sort of stuff, but it is definitely possible inside of nTop. It's a great question. One of the workflows I really like to see. All right. Make sure I'm not missing any questions from you guys. Okay. All right. So again, this is a really awesome perforating holes normal to the direction. You could take this even further, actually, and it doesn't need to be perfectly normal if you want to offset it in one direction. Totally possible inside of nTop. One other thing I saw asked a lot inside of our Slack channel that we have with you guys. And again, if you're not a part of that, please do join and ask your questions. We'll get to them as fast as we can. We want to help you. Will you have access to these files afterwards? I'll have to double check on that, but I believe we'll have access to a couple of these files for sure. What I want to talk about here is taking this stress analysis that I ran on this brake pedal, and how do we create this variably thickened lattice structure. Our field-driven design that we love to talk about. How is it done? How do we do it? What's going on behind the scenes here? So if we grab our static analysis and zoom in a little bit, we can see that our areas of high stress are denoted by these yellow, and our low are by the blue. Now we have these values here given to us by our static analysis, and we can use those if we create a field from it. So we're taking our static analysis, creating a field from our results here, and then we're going to use what's called a ramp block. So what this block is doing is, if we take a look at this slide I have here for you, the way it works is, think of it as a linear interpolation, where we define on this bottom axis here, we define two values. We define our minimum value, which if we look at our picture on the left-hand side here, is going to be distance from this sphere. So we say something like at 1 millimeter away, we want the thickness of our beam to be 2 millimeters. So as you get to 1 millimeter, the thickness of this beam will be at 2 millimeters thick. And then when we're at 10 millimeters away, we want the thickness of this beam to be 6 millimeters thick. And you'll notice that we flatten off the top and bottom here, so it's not an indefinite interpolation where you define the maximum and minimum values. So if you're any closer than, say, 1 millimeter to the part, that entire region will be 1 millimeter thick. Or if you're any further than 10 millimeters away from your part, that region will be your maximum thickness. It won't continue on. It's not an infinite growth. So what that looks like here is where we have the thin structure here, and it radiates outwards according to the field of that sphere to get our thickness. And if we take a look back into this nTop file I have here, what we're doing is saying at a value of 0 pascals, so if there's no stress in the part, we want our output to be 1 millimeter. So we want our lattice to be 1 millimeter thick where there's no stress, and we want our lattice to be 5 millimeters thick at a value of 1.2 times e to the 7th pascals. And what that looks like here is here, where we have at the values of high stress, if we toggle this on and off, at the values of high stress, we have the thicker beam. And the values of low stress, we have this low 1 millimeter thickness beam here. And you can change these values pretty quickly, pretty easily. You can change this to 8 millimeters just to really exaggerate it for you guys. You notice it's rerunning everything for me. So not only am I changing the thickness of my lattice here, it's going to reapply it, rejoin it, re-boolean and refill it every single corner here. So now you can really see how easy it is to control those parameters of your lattice with our ramp block. All right, so I had a question more on the topology optimization side that I want to address for you guys real quick. The question is, I'm doing some topology optimizations and I'm getting some results that, there's pieces of my part that are disconnected. And, is that a result of bad boundary conditions or bad setup or bad loading cases? And that's all totally possible. If I go ahead and show you this file I have here. Now, optimization is only as good as the assumptions you made, right? So this is optimized for the very narrow load cases you defined, where I took this bracket here and I wanted to lightweight through optimization the internal volume of our bracket. I did that by applying forces on these two faces while holding these 4 faces completely fixed. I did a structural compliance optimization where I wanted to maximize the stiffness of this part while reducing the weight. We create our mesh, apply our boundary conditions, and we get a result that looks a bit like this. And you can see there's parts here that, they're missing. They're not right. And you can see there's this big region out here where this is where it's fixed. Why isn't it there? That would be just due to a couple different things, where maybe the volume fraction you specified was too low. You said you wanted 20% of the original volume remaining or less. Maybe that's just too much volume to take away from this part. Maybe that's incorrect. Or if you want to keep your result because it's pretty optimized, you can come up to this threshold slider. And this threshold slider is going to allow us to see the different threshold values assigned to each element by the topology optimization process. Now, what does this mean? We're not overriding, well, we are overriding our volume fraction, where we're adding more material than the 20% or less that we wanted. However, that volume fraction, as I stated, is only as good as the assumption you made for it. Maybe 20% isn't enough, but now you say, I want to add a little bit more material to strengthen up my part. Now I have to run an entire another topology optimization, not an nTop. In nTop, you have that ability to come up here to the threshold, which is just increasing or decreasing the value of the threshold to get those extra elements. Then you can take this part and you can smoothen it out and replace this geometry that you want back for the connections. You might be asking, hey, Evan, why didn't you use passive regions? That's a perfectly valid thing to do inside topology optimization. It's the common thing to do inside of other softwares. Why didn't we do it here? You don't really need to use passive regions inside of nTop. You can see if we go back to our raw result here, we're missing some stuff. These mounting holes aren't closed. There's a couple other sharp edges and pieces that are missing. And that nice frame that we had is gone. Why didn't I make that all passive? Because inside of nTop, you'll see here, it's one operation where I turned this into an implicit, smoothed it, and then used a Boolean union and put our nice smooth geometry back with that geometry we wanted to keep. It takes about 2 minutes to do, so there's no real need to create a passive region when you can just put exactly what you want back right away, not have to worry about smoothing out the regions that might be left over from the optimization. It's back, it's crisp, it's clean, and it's good to go. And you can, again, control those fillet radius just to avoid any extra stress concentrations. So inside of the topology optimization realm, we offer quite a lot of power and a lot of control over what you're doing and your results there. I hope that answered your question. How do you know, sorry, there was a question that came in. How do I know if my laundry fits my lattice fits my boundary conditions? So if you're thinking, hey, I have this force, I have it fixed this way, and I want to simulate this lattice I created to make sure this part doesn't break. How do I know that this lattice is proper? Well, the way to do it is to do what we did in the beginning here, is take your lattice and your whole part and re-simulate it against your original loading case. And that may, result in, this part fails, this part breaks. And that's just a sign to say, maybe this isn't thick enough. Maybe I need to strengthen it up. And that's where that field-driven design can come in, such as the brake pedal that we took a look at, where here, where we said, the uniform version of this here isn't quite enough. The uniform version isn't quite enough. So what we want to do is we want to take it and we want to add thickness and strength where the stress is higher, so that we add the material where it's needed. So there's a couple different ways to go about that, but generally the way to tell if your lattice is proper is to re-simulate, or to print it out, test it in real life and see if it breaks. But generally you're going to want to re-simulate first. Let me open up the chat again, take a look. All right. It seems like I helped you a lot in pointing you in the right direction. Glad to hear that. Again, if you have any more questions coming up, put them in that Slack. Another thing I want to mention, well, first off, if you guys have any other questions, please ask them. I'm going to try to answer them for you right now. But what we're doing is this question of the week, where every Friday we're going to select one really good question we find inside of that Slack or any other place that we get it. We're going to post a answer with a little bit of more detail on how to solve that problem or what's going on there. So please join our Slack here at this, at this URL down here. Please join our Slack. Ask those questions. We're going to be posting these every Friday. It's going to be a really awesome resource for you guys and something I look forward to working on. Another thing, if you want to learn more about different aspects of our software, which I hope you guys do, come to our website, ntopology.com. Under resources, we have blogs. I mentioned that topology optimization blog. Please, if you go there, you'll find all the blogs that we posted on the different articles. You go to events, webinars, videos. If you come to videos, you'll see we have quite a few posted here from just the last week. But we're actually doing 3 live videos a week. So Monday, Wednesday, Friday, we're always going to have a live video. And we're going to be posting them here with the files afterwards. But not only those live videos, we're posting other support articles and other things we found inside of nTop that might be helpful to you guys. So please come here, check out all this material. Everyone's stuck at home, so you got a lot of time to consume all this. It's a really awesome resource. Please take advantage. Also, on the 23rd, we're going to be doing a essentials workshop where I'm going to be talking, going step by step through exactly how nTop works, going through the entire block system here, how to deal with these blocks, how to turn them into implicits, creating lattices, all that sort of stuff. We're going to explain everything about how nTop works at a very lower basic level to get anybody started that needs help. All right, we've got a couple more questions coming in. The tutorials also, sorry, I forgot to mention this guy here. If we come up to our support, go to this tab here, we have quite a few tutorials going on down here. So if you want to say how to do exactly what I want to do, maybe it's on here, you know, but we'll have exactly a tutorial, step by step, how to do it, how to create an FE mesh. You can come here. We're going to have a tutorial with some videos and steps on exactly what you need to do to create that workflow. All right. All right, let's see here. Oh, okay. So there's a good question coming in. So how do I take into account my machine's limitations, such as overhangs or feature size? And that's going to come down to a lot of engineering knowledge. We are always bolstering out our simulation abilities. So we're always going to be having new things inside of here, inside of our static analysis, inside of our topology optimization. We're always working towards this to increase it, giving more different types of constraints. You'll see we have volume fraction, stress constraint, where you can say we only want this to reach a maximum value of 500 pascals, or what have you. We're always working on more. I believe we'll have quite a few more coming out in the coming months and years. It's something we're always working on, but right now you got to think about it before you start designing, right? So your layer height is something like 20 micron. Don't give your part a feature that's a single micron thick, because you can't print that. But a lot of it's going to be possible to design around inside of nTop as well. But we may not have a specific thing that says don't let this get below 2 microns thin. But if you see that, you can come in and you can add in your thickness, like I showed you with that threshold slider, or you can come in and you can actually add in something like a cylinder somewhere if you need to. If you want to add an extra beam for support and thickness, this is in implicit format. So is our final option here. So you'd actually be able to come in here and add in this cylinder for added support at any point that you need it. So if you have a beam that's a little bit too thin, you want to thicken out, there's a couple different ways you can go about that. All right, guys, keep asking questions if you have them. I'm here to answer them. You guys are asking some awesome questions. On the support structure side of things, we do have the ability. We're not a print prep software. We're not trying to replace any print prep softwares, but we do have the ability to take a look at overhang regions or places that might need some more support, where you can use our support region, support volume. And what this block does is it put in your body, you give it the build plane. So if you know you want to orient your part in the positive Z direction or anything of that nature, turn this guy back on. If we know we're printing it in the positive Z orientation here, you can define your build plane, your feature size, and the maximum overhang that's going to look for. So you say 45 degrees is okay. It's only going to show you areas or put that support volume in areas that are overhanging further than 45 degrees. So this is a good way or a quick sanity check to just see how your design is in terms of support structures. All right. Well, thank you guys for coming out. I really enjoyed answering your questions today. If this is something you'd like to see in the future, please go ahead, let us know if you enjoyed this session. Again, join our other upcoming events, such as the 23rd, the nTop Essentials. Monday, Wednesday, Friday, we have those nTop Lives that we're pushing out. We're doing a lot of awesome content there. If you have any questions or you need any more information, again, join our Slack channel. Happy to talk to you. Sorry. So there's a lot of ways we can get in touch with you guys, but we'd love to hear your thoughts, opinions, and questions that you have about our software. They really help out, and we really enjoy making the software better for you guys. And we can give it just a couple more minutes, another minute or two for more questions to come in. A couple more things coming on in. Let me double check these guys. Of course, I don't mind any more topology optimization questions. Keep them coming. I did some research in top-up, and I love the topic. Okay, question about the boundary conditions inside of top-up. Let me just touch on this briefly. I don't want to get too in-depth with this because we can talk about it for an hour. But the question is, when to use what filter type? So what solution type do we want to use down here, where it's our filter boundary, Dirichlet, Newman. There's different points in times when you want to use different regions, where sometimes you'll get this error where it's saying you shouldn't be using Dirichlet, you need to be using a different one. What's happening there? What's happening there is sometimes if you only have, the way the Dirichlet works is, or Dirichlet, if there's not enough elements where you're applying your boundary conditions, it's enforcing a zero density at those boundary conditions. But if there's only a couple elements, it's not able to actually enforce its constraint that it has baked into its solver. So sometimes you'll need to use the other solution type, which keeps material more to the outskirts of your boundary. So if you need to use a different one, or you might have to refine your mesh to get some more elements or thicken up that part, where if you have something too thin, it's not really able to optimize such a thin plate. So it struggles, that optimization method itself can't handle that. That's very high level look at it. If you want to know more, I would suggest taking a look at the actual specifics and the mathematics of that, those solver conditions. And if that's something we'll talk about and see if we can get a little bit better answer for you in the future. But I hope that helped in a general sense. All right. All right, there's a question about remapping fields. I would have to say I'm not the absolute expert in our remapping field area. However, if we go back up to our website here and we go to where we're housing our videos, to take a look at this nTop live video, my colleague Gabrielle Thelen, an application engineer just like myself, did an excellent job describing the remaps and how that works. So please give this video a watch. It's a fantastic explanation with a really awesome use where she does some work with some gyroids to it. I really, really highly recommend that. That's definitely the resource I would use there. All right. Question came in, is there a way to share implicit bodies without sharing their modeling process? And what I think, the way I'm reading that question is, can I take this final part that I have here without sending all of this part here with all the topology optimization and FE boundaries and all that sort of stuff to directly export a implicit body is not currently supported. I'm not sure about the plans for that, but right now we could not right click and export this. The ways you could get this to someone else is turning this into a really fine mesh, something like an STL. If you needed to send to somebody, send it to them, really fine STL, then inside of nTop, they could convert it back. There's a couple different ways, but you cannot directly export an implicit body and share it to them. You would have to send them this file. But in general, we really keep these files lightweight. So this file would maybe be a couple megabytes, maybe 100 megabytes, nothing too crazy that would slow down with file sharing or anything of that nature. I wouldn't worry about file type size too bad. All right, I'm just double checking I didn't miss any of your guys' questions. All right, guys. Well, thank you again. Thank you for coming out. I hope you enjoyed this session. If I did somehow overlook your question, please join that Slack channel, ask it. We'll definitely get back to you with an answer on that. Join some of our upcoming sessions, all those things I mentioned today. Again, thanks for coming out. We hope you guys enjoyed and have a great time. Have a great day. Stay safe, everybody.